So the important thing here about this part one, where we're going to look at linear growth, is that what we are dealing with here is not a model of a biological process, but actually a theory, a mathematical formulation of what we assume is going on in some context. And this theory tells us that some volume that we are interested in, and when I say interested in, it means this is something that can be measured and where we want to have some deeper understanding of, in this case, if it is changing over time, why it is changing and how it is changing. So that volume is given to us by the mathematical equation underlined in yellow in this slide here. And what we can see is that this volume is calculated as a sum of two things. First term that contributes to the volume is the initial volume. Means we have a reference point or a starting point, something that defines an initial state before any changes have happened, sort of set the starting point of our observations. And to this is added a second term, which is the product of two things. So the first thing in here is the growth rate. Translated, it means this is a number. Right? The growth rate is a certain number, and this is multiplied with an entity called t in this case, which we interpret as time. If there's going to be some changes over time, then we can express changes over time as this product of growth rate, the number growth rate, times the independent variable t, which is a linearly growing entity. Taken together, these two terms additively contribute to the volume, and this is our theory that this volume of interest is growing over time as described in this formula, and we can see that it matters at which point in time you are in order to find out how big is the volume at that time point. So we have an example below where we can see that for the initial volume and for the growth rate, two numbers have actually been plugged in. And if we plug in numbers, then they also come with units. We can see that the initial volume is just as given in units of volume, so in this case some micrometers to a cube. And the growth rate is a little bit different in the sense that it actually needs to be multiplied by time in order to contribute to the volume. So growth rate, being a rate, means it will be the volume changes over time. So we divide cubic meters, micrometers by a unit of time, in suggested minutes here. The only thing we need to know is that we need to know how the units of time are defined. So we can arbitrarily choose something, like here we chose minutes, but you need to be clear what you mean by units of time. So this is our formula, and it shows us that there will be a growth over time, and we can use MATLAB to implement this formula, implement this function. It's a linear function of time in this case, and display it and get an idea of how this volume will evolve over time as an expression described by this function. So let's do just this. And in order to do this, I take away the slide and open my MATLAB window. First exercise, implement this function and make a plot of this function volume depending on time, and let us understand how we can use a certain MATLAB function in order to express this. Maybe you've noticed that the word function now has appeared twice in the previous sentence in different meanings. So just, of course, it might be obvious from the context that we are not referring to biological function when we say function here, but also between mathematical and computational function is a big difference. Mathematical function was the entity described by the previous formula. When we refer to a function in MATLAB, we have an algorithm that implements certain procedures that we want to happen. It can be used to represent a mathematical function. Maybe you have learned the initial steps with MATLAB by displaying the sine wave. So that would be the implementation of a function, but we can also use it to express other things like numbers and combinations of numbers. So we are not going to put our things into function files today. We are going to work entirely in scripts, and we have it organized such that first we look at the slide what we want to do, as we did just now, and then we go into MATLAB and we open a new script file and implement the things that we need to have in code that can be executed directly without function calls. So in order to express linear growth, we need to put a comment first. First, we need to define the function and how we go about defining a function. So if we have something called linear growth, which we might call lin sub growth, that would be the name that we assign to this function. First thing to be aware is what is supposed to change. So if you remember from the previous formula, we had two numbers and time. And if we want time to change, like linearly growing time, we have to define that. And we do that by putting t, the symbol t, in round parentheses, following the @ symbol, where @ is shortcut to refer to the function that is going to the entity that is going to change in that function. And we'll have that modified in a second. And then we remember there was this initial volume, and I just plug in some number. It was suggested to put in 0.4 and add the second term, which was 0.2 times the entity called t, or time as we interpreted it. So that's enough for a function definition. It's a so-called anonymous function, and it helps us to make this function available for any point of t that you wish to evaluate the function at. The output of the function, in this case linear growth, will be the volume. So we might have also called it volume, but I just refer to linear growth to stress that we are dealing here with the implementation of a function, as opposed to a model which we're going to have later. So if we do this, we can then use another MATLAB function called fplot, followed by the round brackets that indicate that we need some argument to put in order to make a plot of the function that we have defined. So of course we have to tell the name as one argument. This is linear subgrowth. First argument, so fplot will take that function, but fplot needs a second argument. It needs the limits of the variable, lowercase t, over which you want this function plotted. You have to put that into an array, and the array contains two numbers, and it's the initial number. So if we start at t equals 0, we put 0, and if we want to calculate up to a time equal to 20 minutes, we would separate it by a comma, putting the number 20. This is now the code to define and plot the function, and if we just execute it, we can check it for bugs. There's no bugs disappearing. Instead, MATLAB opens the window directly. And in order for you to see that, I need to open my window. And when you can now see the outcome of the simulation, you can see a graph, which we can annotate in order to describe what is going to be seen here. The X label was our time t, our variable t, and on the Y label would be the volume. So we have volume as a function of time, and this is a function describing linear growth. The volume grows linearly over time. What we might also notice, if we look at the scale of the y-axis, it doesn't start at 0. If we correct the y scale to start at 0, we can see that the initial value at time equal to 0 is different from 0, and of course it's 0.4. If you look at the code that produced this graph, 0.4 was the initial value that we started with. And we can see that fplot helps us to see that range from 0 to 20. We can see linear growth. So we can also find out where it stops. It stops at 4 point something on the right-hand side corner. And fplot is even more convenient. You can also use it to evaluate the exact volume at a certain time point. Now, how would you do that? If I just clear my screen, my function called linear growth, which I have defined here, can take an argument, namely the time. And if I say I want to know it at time point equal to 20, say 20 minutes, then executing lin growth at 20 will give me the exact volume, which is in this case 4.4. Might be micrometers cubed if we had it defined like this, but you can see that it will be possible to do it for every time point. We can check 0, we can check 20, and so on. You can also check for multiple values. This is something which is not explained in the material. How would you do that? I clear my screen. What if we wanted to know multiple values? We could just put in an array of numbers. So we could try to find out all the values between 0 and 10 that linear growth can take in steps of 1, and we'll get those numbers returned in an array. It's an output array which then tells us what is the volume at time point 0, which is the first entry, what is the volume at time point 10, which is the last entry, in steps of 1 in time, so in steps of minutes. This is just to say that this function definition is a very general thing which we can nicely use in order to access features of a function.